Kerry.
Excellent. Thanks so much, Liz. And great to see so many people online. I'll just start by acknowledging the traditional owners of where I'm joining the webinar from the Turrbal and Yugara people here in Brisbane. And I recognise the traditional owners of all the countries where you're working from today and teamsing in from. So thanks, Liz, to that introduction, and also a thanks to Suzanne, who's chair of our advisory committee, for guiding the assessment of the research projects that we're going to hear about today. We saw the projects also through our committee, the steering committee, and it's a really strongly competitive field. So well done to everyone that was awarded a project in this last round. So I guess it's probably not lost on you guys that it's a really important time for decarbonisation in our state. Our Minister for Energy recently announced the delivery of an energy roadmap and also of sector emissions reduction plans to set us on our pathway to net zero by 2050. I won't talk too much about that now, but because Liz Fellows, one of my colleagues from Queensland Treasury, and also a member of the steering committee for the Decarb Hub, will go through all of that in a few weeks in another webinar. So please come to that and get insights from the central agency, where the powerhouse of all this activity now. But internationally, nationally and locally, from my perspective, there's never been a better time to have evidence informing our policies, particularly our environmental policies, and ensuring that we're carefully considering all economic, environmental and social aspects of those policies and of our decarbonisation journey in particular. And thankfully, that's what the Decarb Hub was set up to do. So we are ahead of the game in that regard. And as chair of the steering committee for the Decarb Hub, it's been a real privilege to watch the establishment under Greg's leadership and the pulling together of the expertise across our state. And it's really going to be brought to bear over the coming year to 18 months. So it's a really critical time. And we are well placed. We have the foundations in place for our expertise in our research institutions to inform the future. So we'll hear from 8 projects. And what excites me about these projects are the diversity of topics and disciplines and expected outcomes that we are seeking from those projects, and that the usefulness of those outcomes. It's not just for government, it's for industry, and it's for our communities. And just, the diversity I mentioned before, we've got projects that are funded now through the Hub that will enhance our understanding of community attitudes, of our workforce, of protecting wildlife in a renewable energy future, benefits to our health and enhancing those, to name just a few. So there's a really nice cross-section of disciplines represented. And also the other thing I was really pleased about is the diversity of collaborators on these projects. And that's, the essence of the Hub is Team Queensland. The essence of science in Queensland is Team Queensland. So having that kind of collaboration bedded into these projects really speaks to that aspiration. So thank you, Liz, for joining the Hub. An incredible asset to have you come over from Queensland Government into that leadership role. And you and Greg, I guess, you make a power team. So it's, really looking forward to, the next 6 to 12 months and seeing how you pull it all together. And I guess also just I'll finish by saying thank you to you all. We have a small number of people really represented here in this call that is the expertise that we're seeking to draw upon across Queensland. So please continue to network on behalf of the Hub, bring other people and other expertise along, that will only enhance the impact of the research that we're all doing, the more inclusive we are of our colleagues in this as well. So thank you, and I'm looking forward to hearing about the project. So back to you, Liz.
Thanks, Kerry. And I just want to acknowledge the leadership that we've had with Kerry as the chair of our steering committee. It's really added a degree of confidence to us as we've been navigating our way through the complexity of the research challenges. So without too much further ado, I want to introduce Professor John Rolfe. Now, John is speaking today on behalf of Jeremy de Vlack, and I hope I've pronounced Jeremy's name correctly, who are doing a project on transitioning to net zero, exploring preferences and regional strategies for decarbonisation in Queensland. So, John, if you're here, and I can't see everybody, so do you want to put your screen on, and then I will navigate to the PowerPoint and share that as a screen?
Okay, thanks, Liz, and thank you, everybody, for attending. What I might do is I'll share my screen, but I'll share a different screen to begin with. So I hope you can see this. This is a map of all the renewable energy projects in. This is a snapshot of Queensland. We're accessing a database that's got all.
Okay, thanks, Mandy. Bye.
We've got a database that's identifies all the renewable energy projects in Australia, and we can narrow it down to Queensland. So we've already collected a lot of the database, but we're cross-matching it with this other database called RenewMap. So that it gives you a bit of a snapshot of the amount of activity in this space already in the state. So I'll just move out of that one and go to my PowerPoint slides to introduce you the topic more formally. I hope that's come up. And I'll just go through very quickly because I'm aware of the 5 minutes. So the reason why we're doing this project is there's been a lot of questions about what the workforce implications of the change from our existing energy generation in Queensland will be to the renewables. And there are two big reasons for that. One is that there are implications of those workforce needs across the region. So some regions like Central Queensland, we produce about 53% of the power in the state at the moment with a lot of workforce, but probably there'll be a net reduction in workforce moving to renewables, whereas Southeast Queensland and probably Northern Queensland will have a net gain. So trying to map that change in workforce is really important. The second big reason is that this move towards decarbonisation is going to require a lot of skilled workforce. So trying to identify where the workforce is required is also really important to manage that process. So what we're doing, we're identifying all the solar and wind farm projects in Queensland. Now that includes those that are already commissioned, those that are under construction, and those in various planning stages. And then we're going to each of those projects, identifying what their construction and operational workforce requirements are and building a database. And then we're using regression analysis to identify whether there are differences between the different types of projects, the stages that they're at, and in the different regions that they're at. There's two of us doing this work, myself and Kalpana, who works in my group. Kalpana's at another workshop today, so she couldn't be part of this session, but she's basically doing the bulk of the work. And I'm an environmental economist, Kalpana's an environmental scientist, so we've got pretty good skills to match this project. And just in conclusion, I just want to give you a bit of a picture of some of the data that's coming out. We've compiled the data on the wind projects. We're still working through the solar, but what's clear is that compared to the number of projects that are already operational, there is a huge pipeline of new projects coming through under construction and in various stages of approval. And most of those are in North Queensland, Central Queensland, Darling Downs, with some in far north and some in the Mackay Whitsunday region. And if we look at the generational capacity is huge in North Queensland, that's the Townsville region, Central Queensland, Darling Downs, a little bit less in the Mackay region, and very limited everywhere else. So if that's going to be quite a change in where the generational capacity is at the moment in the state. And just looking at the workforce requirements, roughly in the different regions at the different stages, up to about 4,000 construction jobs, but the operational jobs are much lower. So probably peaking at around 250 or 300 in each region for wind. So one of the messages coming out is that the operational workforce in the regions is going to be quite limited compared to the footprint of say, coal-fired generation. And I'm happy to leave it there.
Thanks, John. Are there any questions from the floor? I might ask one if there's nobody else asking any questions. Is part of the project looking at the way in which those construction needs in particular are a potential barrier to success for the projects, like looking at those very significant numbers that are required for construction? Is that something you're looking at, or is it a different focus?
It's a different focus. Most of the construction workforce is very much fly in, fly out, or drive in, drive out. So the construction workforce is very mobile. We don't at this stage have any insight into where the construction workforce is coming from. Whereas the operational workforce is much more regionally based. Just to give you a bit of context, the Queensland Government a couple of years ago released this report about employment in the renewable energy sector, and they suggested that the total impact on the Queensland workforce would be more than 100,000 jobs. Now, those figures are huge compared to what we're actually finding. So the operational workforce will be between 1,000 and 2,000 people across the different regions. So the workforce implications are much lower than what has been projected by the government, even when we take the sugar hit of construction workforce into account. You know, these projects take about 18 months to build, and then the workforce goes somewhere else.
Thanks. Is there any other questions before we move on? Happy to keep moving if not. So John, you're getting a double, what do you call it? A double, it's like a double whammy, presenting on the next one as well. So if you want to just move straight into the project that you're leading, that'd be great. Thank you.
Okay, I'll go to the next project. So, oops, I've just got to escape out of it and share my slide. So sorry, I gave you I did this in the wrong order.
Oh, the wrong order.
Liz? Yeah, sorry, because I was focused on my own. So I've already talked about the project that I'm leading, which is the one on the workforce. The other project that I'm involved in is led by Jeremy, and he can't be here because he's running a workshop today. But it's about looking at the regional preferences for decarbonisation. And in some ways, the order that I've presented in is a nice segue, because the workforce project is showing that there will be quite large changes in workforce in the region. So the Central Queensland region will probably suffer a net loss in workforce moving to decarbonisation. But say Mackay Whitsunday, the north region like Townsville, they will generate net gains. So what we are interested in is working with different regions to identify what their priorities are around decarbonisation, looking at these potential transitions and impacts. And we're looking at things like the different employment outcomes, the impacts on industry, the amenity benefits, and the opportunities for new industries. So we haven't finalised what the different criteria will be, but those are the sort of things we're thinking through. So what we're going to do is to compare two regions. We're going to work with the regional populations in these regions, so Central Queensland and Northern Queensland, and try to identify the extent of support and where there are potential drivers and barriers towards concepts of decarbonisation. So we're wanting to check how strong the public preferences are for the different energy transition policies, and then develop some recommendations from that. We've got a bigger team in this project because it's a lot more complicated. So Jeremy's the lead. There's two of us from CQU, so Jeremy and myself. We're going to be basically running a more quantitative analysis using a technique called choice experiments, where we actually offer people in each region a snapshot of the different potential outcomes and get some feedback on that through different choice profiles. And then the James Cook University team, that's Alan Dale, Harriet Babicon and Jenny McHugh, they're going to work in each region with focus groups to get some different perspectives on what people in the region see are the challenges and opportunities. So we've got 5 objectives. So we want to understand the trends in the transition. So we're looking there to identify what the issues are that we think are going to be relevant. We want to identify what the priorities might be, and which sort of relates to the issues, but we'll work with the focus groups in the regions to help identify those priorities. We'll try to narrow the factors down into about 5 groups, which are limited, identified there under number 3. We're going to run some workshops in each of the areas to identify attitudes and preferences. And then we're going to run these experiments, which will be run on the internet, offering people some different profiles of where the decarbonisation options could be for each region, and see which ones they like to support. So we are only at the early stages in this project. We're hoping to use the results out of our workforce study to be able to provide inputs into this second project about the regional preferences. And we'll be basically doing some focus groups and then designing our survey. We'll run the survey and then run the workshops and interviews, particularly both in North Queensland and Central Queensland. And we should have some results to start to provide through the hub towards the end of the year, with the final wrap up early in 26. And just as a final slide, here are some examples of work that we've done at this high level. These are choice experiment profiles for the Great Barrier Reef, where in the bottom right, you can see we've asked we asked about 2,000 households in Queensland what support they would offer to protecting the Great Barrier Reef with these different trade-offs for coral, seagrass, recreation and tourism. And that helped us to provide some outcomes about what people saw as most important in these different factors. And we want to do a similar thing with decarbonisation. Okay, I'm happy to leave it there, Liz, in the interests of time.
Fantastic. Thanks, John. And again, are there any questions that people have to ask John about his research project? And because these projects are at the beginning, there may be less questions. Some might generate more, but just looking to see if there's any hands coming up. If not, we might just keep moving on. So the next presenter is Distinguished Professor Lynn Schwarzkopf. I think I've got that pretty close to, there's just wondering what the CQ region definition is. So, John, before we head to Lynn.
I'll just address that in the chat.
Okay,
Liz,
thank you.
Keep going. Yeah.
Thanks, Lynn. Sorry, apologies for that minor interruption, but so Lynn, if I hand it over to you, if you're happy to run your own PowerPoint, I'm fine for that, but I also have a version of it as well, but it looks like you've got it. So
can you
handing over
see
to
that?
Lynn.
Yeah.
Yes.
Okay. So you can see that easily. Everyone can see it. I think I have to minimize you guys. I don't know what happens if I hit this X. Maybe that's bad. Show more people, show only me.
It's fine
or
from
you-
our end, Lynn.
you
we
can't
can
see
the
that.
PowerPoint.
Okay, that's
yes,
good.
Thank you.
Okay, so what I'm talking about today is what we think is an important opportunity to use solar farms for biodiversity preservation. And the team is here today. So Miles is here, Miles Menz from James Cook University, and Eric Nordberg from UNE at University of New England, and me, and I'm from James Cook as well. And there's also Sebastian Hofer is also here, and he is doing some of the work for this project. So we're all here in case people have questions. So as we've been talking about, renewable energy is a growing land use worldwide. And as we decarbonize, and I hope we keep decarbonizing, we keep having increased renewable energy. And in Australia, as we just saw, renewables are growing really fast, and these are, just like the other slide we saw, these are a whole bunch of new projects that have started and their size and approved projects as well. So it's just growing like topsy. And what happens is when you want to do these projects, their land use decisions arise. And so large cleared areas are really good for solar farms. And this is an example of a large cleared area covered in sheep. And the land from large cleared areas like farms can be purchased or leased relatively easily. And as a matter of fact, it can be double use. So livestock can graze under the panels, so it can be easily used. By comparison, using greenfield sites is more difficult because large cleared areas are better for solar farms anyway, but using a greenfield site is expensive and time consuming to clear, and there's more red tape involved in using greenfield sites. So it can be better to construct solar farms on farmland that maybe isn't so valuable anymore. So solar farms are often constructed on poor quality, previously cleared agricultural land. We get a nice picture of a weedy bit of land with a lot of bare ground here. And it has fairly low biodiversity value. So solar farms may actually help rehabilitate land like that. So there may be a win-win in there. Now, we're not the first people to do research on this. There's research from the USA and Europe and the UK, but it focuses really heavily on pollinators and on vegetative biodiversity or vegetation biodiversity. The Australian research focus has been on grazing and on weed control. There hasn't been any data from tropical systems, and as somebody just pointed out a minute ago, John just pointed out a minute ago, a lot of this growth is in North Queensland in tropical systems. So it's interesting to find out what's happening there in terms of biodiversity. So for our project, what we're planning to do is work on Ross River Solar Farm, and this is a picture of Ross River Solar Farm, And we're going to sample biodiversity, and these little squares stuck all over the place are examples of sample plots where we'll sample biodiversity on the farm and on adjacent farmland areas, and we'll compare biodiversity in those different areas. We're going to measure biodiversity using all the different ways you can do that. We'll use various traps, and these are traps for insects and invertebrates. There's no insect trap here, but these insects fall in these ones. We'll have camera traps, and this shows you a kangaroo checking out a camera trap. We'll have acoustic recorders recording the sounds of birds and other animals, amphibians, and also mammals. We'll do bird watching so we can see what's present on the site that we can't hear, and we'll do spotlighting at night to get nocturnal species. So we'll find the vertebrates at the site and also the invertebrates at the site as thoroughly as possible. And what we hope to find out is what biodiversity is supported by solar farms, and we can compare that to the adjacent farms, which may be quite poor quality. And we can make recommendations to enhance ecosystem services on tropical solar farms. So how can you make them better? And we can find out whether solar farms could possibly support more biodiversity than grazing farms, or at least as much. And so we'd like to find out whether solar farms might act as new or emerging ecosystems. And that's me.
Thanks, Lynn. Anthony, are there any questions from the floor? I see a question from Liz King. Liz? Hello,
Thanks,
Liz.
Lynn. We might just send you, DPI has done some work on looking at agrivoltaics in Queensland and a literature review. I suppose we differentiate between sheep and cattle. So might be worthwhile in your work also looking at compared to, I suppose, depending on what other coexistence is happening on the site as well.
Yeah, I think that's an important point. Did you get our paper on agrivoltaics in your review?
So Marie Bowen did the literature review. I'll have a look, but I'll happy to share what she's done.
Okay, thanks. That would be great.
Thanks, Liz. Anyone else got a question from the floor? If you're still mulling over a question, what will happen is that we will have time at the end. I think it's meant to be Liz, but it could be Lynn. You mentioned North Queensland. Are there any specific IBRAs that are targeted?
Sorry, are there any specific what's that are targeted?
IBRAs. And whoever, Mike, you might want to ask that question.
What's the acronym mean? I don't think I've heard of it before.
Where is Mike, who asked the question?
Michael Bell, is that who it is?
That's Mike Barnett.
Oh, okay. Yeah, I
Put up
got
the
him
question.
too. So I can see him. What's an IBRA when it's at home?
Bioregions. Oh yeah, it's the bioregions. I knew that. So you know the big level bioregions across, like that's actually nationally done.
Okay. Yes, we know about the bioregions. We're aware of the bioregions. Certainly the Ross River Solar Farm is entirely on one bioregion, so I think that's okay. But as well as the adjacent land. But Eric actually is doing some work down in New South Wales on a variety of different solar farms, looking at the impact on biodiversity. So Eric, maybe you want to answer about other bioregions?
Yeah, so obviously trying to get kind of regional specific responses is good. So we haven't broken into North Queensland or tropical systems yet, which is the exciting part of this. Whereas most of our work has previously been kind of in this temperate region, but we'd like to expand even further than that into some arid spaces and things like that. But yeah, I think at this point, it's just a matter of finding sites that we have access to in a bunch of those different bioregions. But yeah, it would be great to get data from a whole variety of different places.
Yeah, I could just add to that and say that our major barrier has been finding solar farms that want us to come and poke around on the animals on their farms. And so, yeah, we're restricted in the bioregions because we're restricted in which solar farms we can access at the moment. Hope that answers your question.
And Liz King has a follow-up question, which is, will you also collect presence, absence of feral animal data at the same time?
Yeah, we won't have any choice. Heaps of the animals on there are going to be feral. So yes, we will absolutely record that. We'll try and get abundance as well. We'll be trapping for a period of time, and for some things we'll be able to assess abundance. With ecoacoustics, we can get abundance now by counting number of detections. So we can at least estimate abundance for a lot of different creatures now.
Great. Thank you, team, for introducing your project, and there'll be some more time at the end if people think up more questions. So with that, we might move on to Professor Moham Jacob, who is doing sustainable vegetable cultivation using agricultural waste derived from biochar as the per the screen there. So Moham, I'll hand it over to you. Thank you.
Thanks, Liz. You can see my screen. Okay. Good afternoon, everyone. I'll be talking on the sustainable vegetable cultivation using agriculture waste derived biochar. So roughly around 10 to 30% of the emission is happening from the different agriculture waste. So here the project is intended to utilize the agriculture waste, convert that into the biochar, and then utilize that back into the agriculture. So it is kind of like the circular economy that. So my partners are basically coming from Queensland University of Technology, and also I have a couple of industry partners, and the mandates they will be later on trying to implement the outcome of this project there. Okay. So biochar is a solid product of which is produced from the thermal decomposition of organic matter at high temperatures, typically in the range around 600 to 900 degrees centigrade under the oxygen-free environment that. So it is a stable form of organic matter. It is rich in nutrients and it's slowly degradable. And also it got a porous and large surface area, which is a property we are going to utilize that, particularly for the nutrient retention and also the moisture retention. That it's also got a very good nutrient stabilizing metrics, better than using a compost. That it got like some good properties like water retention, and also it is very good for favoring the microorganisms in the soil there. So when we are using the waste material, typically in this case, okay, we are going to utilize the agriculture waste. We are trying to convert a waste into a valuable resource, and then thereby it is going to reduce the waste, and also it is going to reduce the emission there. Also, it is going to assist the water, particularly like it can retain the moisture. And also it is the biochar is good for removing the organic and inorganic contaminants from soil. Once you apply in the soil for the agriculture, you can basically like retain the nutrients and also support the microorganism activity. So in net effect, okay, like we are helping to basically reduce the emission, and also we can use the biochar for storing the carbon dioxide there. So this is my lab where we basically like got a microwave pyrolysis facility. So this is a custom-made facility. We designed the system ourselves, and we can basically like customize that for whichever the application we are looking for that. So this is the agriculture waste, and then like this is the biochar which is produced from the system. So the system that we basically got, okay, the lab system we produce can process around 5 kilogram waste at a time. Or we basically also scale up that for the Australian Defence, which is around 100 kilogram waste at a time, or 1 ton of waste during a daytime there. The major objectives of this particular project is to develop the biochar using the microwave assisted pyrolysis, and particularly we are going to focus on the hemp-based biomass. The main reason of using the hemp is, okay, it's really good for the carbon absorption, and also the plant growth is very big. It grows to around 4 meters tall in around 3 to 4 months time there. So once we basically get the hemp waste, we convert into char and then plant some of the vegetables in that, study the plant growth, yield and moisture retention, and also like the irrigation requirements there. We also do the economic feasibilities and the scalability study for biochar application. So these are some of the anticipated outcomes of the project. So particularly it is going to support the decarbonization, mainly because it is going to reduce the GSC emission, and particularly during the time of the biochar production as well as for the application time. The soil moisture retention is expected and also will be supporting the carbon sequestration. It improves the carbon soil and could all help to mitigate greenhouse gas emissions. So we will be coming up with a practical roadmap for adoption in sustainable farming. So with the stakeholder engagement and the feedback, we'll be able to feedback on the scalability. Particularly, we'll be able to basically develop a portable on-farm biochar pyrolysis system. So you can process the agriculture waste on the farm itself and then like utilize the same char into the same farm there. We can also have large capacity slow pyrolysis industrial systems. And we can also develop large-scale agriculture implementation there. So that's from me. Thank you.
Thanks, Mohan. Have we got any questions for Mohan and his team? I don't see any hands. There's a hand. Liz King.
Jacob, I'm just wondering if you're targeting a particular agricultural use. Is it horticulture or cropping for the biochar use? I'm just interested in how you propose to apply it.
So at the moment, we are basically going to select few types of vegetables. We're probably going to look into some fast-growing vegetables because, okay, we wanted to see the outcome in a couple of months' time like that and use that to under. So we look into the plant yield, the growth yield, etc. But later on, we should be able to basically like extend that work into different areas there.
Okay.
Thanks. Any other questions for now? No? Thanks, Marlon. We might have some more questions at the end as well when people have had a bit of a chance to think about it.
Thank you.
So now I want to move on to Dr. Mehdi Sarati. Mehdi, I hope I'm getting the pronunciation close enough. Mehdi's obviously ready with his PowerPoint presentation, so I will hand it over to you, which is a beautiful bright green.
Thank you, Liz. You see my screen and you can hear me okay? Yep.
Yes.
Okay. Wonderful. Good afternoon, everyone. My name is Mehdi Sarati. I'm a senior lecturer at University of Queensland School of Civil Engineering. On behalf of the partner investigators and the chief investigators, I'm going to talk about this proposal we put in for the DCAP hub as enhancing CO2 absorption in shotcrete and concrete using mafic and ultramafic aggregates. I'm a geotechnical engineer. My research interests are in rock mechanics, rock fracture mechanics, and design of sustainable construction materials. And I guess we have over the years developed some research data set and some promising outcome mainly related to recycling solid waste as a replacement of sand for construction purposes and CO2 sequestrations in different rock formations. What you see at the upper right corner of the screen is a new shotcrete mix that we designed thanks to the input from the industry over the last 5 years. Those who are not familiar with the term shotcrete, it's basically concrete in nature, but instead of having a formwork, you spray it, which gives you more flexibility in terms of different areas that you can use sprayed concrete. So in this new mix, what you see on the screen, we sprayed in Mankuta. So if you happen to be in Mankuta close to the portal, you see on the left, there are two areas. The top part is where we applied a reference, a typical shotcrete, and the bottom section is where we sprayed this new mix design. We realized that we replace sand in this shotcrete mix with glass aggregate. this type of glass that end up in landfill. So we receive it from landfill, we crush it into the sand particles, and we replace sand with glass at different percentage. It gives us the same workability and pumpability, and we realized that during the field test that it also has a reduced rebound and a now carbon footprint. Another project we have been working with industry partner, mainly from New Zealand. We have been working on CO2 sequestration in mafic and ultramafic rocks. And I guess based on the promising outcome over the last 5-6 years and the research data set we generated, we put this proposal forward and we would like for this to be successful. And I think this information we have generated so far is going to help us deliver the project. So this project is mainly looking at how replacing sand with mafic and ultramafic based aggregate could impact the CO2 absorptions of concrete or shotcrete or sprayed concrete over the lifetime of the project. Well, of course, you don't need me to tell you that concrete is the most widely used man-made material on Earth, and it's believed that around 30 billion tons of concrete is used globally. Concrete has 4 key components. We have water, you have admixture, which gives it's a chemical that gives some unique properties to your concrete, and then we have cement and aggregate. Well, of course, we know that two out of these 4 components are considered to be major contributors to global CO2 emission. We have cement, which is believed to be responsible for around 8% of the global emission, and then we have sand. Sand is becoming the most consumed natural resource on the planet after fresh water, and it's the most important solid substance on Earth. And like cement production, sand mining is also it's a huge it consumes a substantial energy and contribute to the global CO2 emission. But there is when you have concrete or shotcrete or sprayed concrete, there is a beautiful ability of concrete, and that's what it absorbs CO2 from the air during the lifespan. It's similar to how trees and jungles absorb CO2. These CO2 absorptions happens through a chemical process, which is called often sponge effect or carbonation. What you see on the table at the middle of the screen and also on the chart at the bottom right, you see different studies that for a different time period, they have looked at how much emission is happening CO2 emission is happening because of the concrete industry. And then during the lifetime of a project, like 50 or 100 years, how much concrete or shotcrete can absorb CO2. If you look at the last column, it's an uptake ratio. It could be between 20 to 50% of the CO2 emission during the pouring of the concrete and construction of the concrete. Over the lifetime of the project, you can absorb a concrete, which is a very nice, promising number. So although this whole process, like a sponge effect or carbonation, can help mitigate carbon emission, but its full impact, especially as a function of different aggregate have different carbonation property, is largely understudied. So what we are going to do in this project, we expect to receive an aggregate like mafic and ultramafic aggregates from New Zealand, from Oman, and from local suppliers. And we are looking at the grain scale, because those who are familiar with the shotcrete industry or concrete, they know that the majority of the aggregate has a igneous or sedimentary rock in nature. We are looking at this mafic and ultramafic rock, look at the strengths and behavior at the grain scale. Then we mix it at the harden or macro scale, while we look at the carbon absorption of a reference mix and a new mix with these ultramafic aggregates. We also look at how durability of the new mix changes in terms of alkali-silica reaction, in terms of creep, in terms of chloride penetration and sulfide attack. So I think that one of the outcome would be that if you replace a typical natural sand from, for instance, a river, might come from river or a quarry mine with a mafic or ultramafic aggregate, how it's going to change the mix behavior over a long term in terms of its strength property and its in terms of the sponge effect. Yep, that's me, Lisa.
Great, thanks, Maddie. Have we got any questions on the floor at this point? Chris.
Hi, Liz. So just
Hi.
a bit of clarification, because I find this amazing. The emission, comparing to the emissions, so you're saying the emissions in terms of that are generated in terms of the creation of the concrete is then reduced over time through the absorption process. Where's the emissions come from, I guess?
Well, the emission is coming from mainly sand depletion, sand extraction and transportation, and the cement that you need as a key component in your concrete mix here. So this emission is mainly coming from cement as the sand as the raw materials, and then the absorption happens during the carbonation chemical process.
Right. Thank you.
Thanks, Chris. And we've got a question online from on the chat from Lawrence, which is us saying, curious about the relative cost impacts of this method.
Wonderful question. So there are, once you change the aggregate, there are different aspects. You can look at the CO2 absorption, the carbon footprint, the cost, and also availability of this new aggregate. So there are all question marks that we could have included, but we decided not to get too much excited. We decided to let's do it step by step, looking at the durability first and the carbon footprint. And if the results are promising, and then we would consider other like long-term type of access to these materials and the cost.
Great, thank you, Lawrence, for that question. Anybody else before we move on? Great, thanks, Maddie, for your presentation. So with that, we'll move on to Dr. Naoya Takada. Sorry, not Oya. I hope I got pretty close there. Who's talking about optimizing on-farm and carbon footprint measurements for verification of low carbon commodities. So I'll hand over to Naoya.
Thanks very much. My name is Naoya Takeda. I'm a postdoc researcher at QUT. So this project is about on-farm carbon footprint. So in food and beverage companies, they have an aspirational target for supply chain greenhouse gas reduction, which includes the scope 3, so coming from the carbon footprint of their ingredients, which account for a big footprint of the whole supply chain greenhouse gas. And particularly on-farm nitrous oxide emissions are responsible for like up to 50% of the whole carbon footprint of the food supply chain. So this is the biggest portion of the emission target to be reduced for the food beverage companies. However, these N2O emissions are highly variable depending on the environmental and management conditions. At the moment, in the typical assessment, such as like life cycle assessment of these food products, using fixed emission factors guidelined by IPCC, but this cannot account for this variability in response to environmental conditions or management options, and it carries large uncertainty as well. Then it's challenging to verify the reduction, and then at the moment can only be verified by costly and inconsistent field measurement methods. So the need is robust yet low cost on-farm N2O verification method. So this Decarbonisation Hub project targets this optimization of on-farm carbon footprint measurements, and particularly for verifying low carbon agricultural commodities. It's a collaboration between QUT and then UQ, and these research groups have already accumulated a large number of N2O data sets through the previous project across Australia, using automated or semi-automated high frequency greenhouse gas chamber systems. So we have accumulated good quality data across different cropping systems at the national scale. And particularly this project collates these data sets and analyze the primary factor drivers of these emissions with the high temporal resolution, and combining process-based modeling approaches and machine learning approaches. And then these analyses will help us to understand the drivers and uncertainties, and provides the way to gap fill these emissions. And by using these estimates, we can further optimize the end-to-end measurement strategies. And the outcomes of this project will bridge the potential greenhouse gas reduction practices in agriculture and food and beverage companies with greenhouse gas reduction targets. And by providing these verification methods, we can support adding values of low emission sustainability values to agricultural products and industries in Queensland. Thanks very much.
Thank you very much. Questions? Anybody got any questions around the table? Greg.
Yeah, sorry, I'm on the road between Charleville and Augathella. I hope you can hear me. We're actually going to deliver some training about these very questions you're looking at. I guess you were looking at cultivated systems, as I understand, like as
yes.
Farming. I was just wondering,
yes.
Are you extending this to sort of mixed farming, broadacre agricultural systems as well, which is the vast mass of our land space. So just wondering on the extension of that to other grazing systems.
Grazing systems is a very good question. To some extent, we can apply the outcomes of this project as well. So the project, the data sets building, like this project is building on top, includes, yes, broadacres like grain crops, sugar canes, to some extent cotton as well. These data sets can produce like these driver analysis and an answer data analysis, including various environmental conditions, soil conditions. At the same time, livestock system has got like a unique source of emissions, such as like urine patches and like danks as well. So partially yes, but then there will be probably additional gaps to fill to apply the findings to like grazing systems. But yes, that's extended scope, I would say, yes.
Thanks for that question, Greg.
Thanks very much.
Lachlan has got a question on the chat, which says, will an output be more accurate emission factors?
Sorry, can I, sorry, maybe.
Will an output be more accurate emission factors?
Intention would be yes, to support or to make it more, to account for the interaction between environmental conditions and management options. So in a way, yes, the output may not be in the form of like a factors, more like functions of emission estimates. But yes, that will contribute to improvement in emission estimation to get together with this management, measurement optimization, but also that will contribute to, yes, improvement in accuracy of the emissions, which is currently based on emission factors mostly. Yes.
Great, thanks for that. Are there any other questions? No? You might get some more at the end, I think. So we might move on now to Kathy. So Professor Kathy Yule, who is Team's project, is on unique fire-resistant Queensland peatlands and nature-based carbon storage solutions. So Kathy.
Yes. So my colleagues and I are studying carbon sequestration in the coastal peatlands of southeast Queensland. And surprisingly, until recently, it was thought that peat was really uncommon in Queensland. But we, and also Patrick Moss from QUT, have been working on this and discovered extensive deposits in peatlands like this one you can see in the slide. And also there's a different one behind my head you can see on the screen with me on it. And these are on Gari, used to be called Fraser Island. Next slide, please. Oh, sorry. And this is globally significant because peat is a precursor to coal, and so it can sequester carbon for millennia. But peat is also highly flammable, and this is problematic in Australia because it's the world's most fire-prone continent, as I'm sure you know. So these peatlands occur along the coast and the offshore islands, such as Bribie and Stradbroke Island, Moreton Island, and you can see it not so clearly on the map, I'm sorry, it's a bit small. But they go from Byfield National Park down to northern New South Wales. And from the air, you can see the middle picture. This is what they look like. And in the right-hand picture, you can see us at Duck Creek. Actually, those little dots are us sampling the pools. Next slide. So we've studied over 20 of these peatlands on Gari, and there's many, many more along the coast and the coastal islands, as I mentioned. And we've found peat layers up to 8 metres deep. Patrick's found some even deeper on Stradbroke Island. And they're dominated by the peat-forming wire rush, which is called Empedisma minus, which you can see here on the left-hand side. And this is a particularly interesting plant because it's both resistant and resilient to fire. It has roots that grow upwards and form this incredibly thick water-filled mat that covers the entire floor of the peatland. And it actually protects the peat underneath from fire and drought. And then it has underground rhizomes, so it can resprout straight after fires, like within days and weeks after the fire. And you can see on the right-hand side, this was Uran Creek and Gari. The top picture shows it after the wildfire of December 2020, when a lot of Gari burnt. And this was one of the worst burnt sites. And much of the peat was destroyed. And you can see sand showing. Actually, the peat got burnt completely away. Yet 7 months later, you can see the Empedisma growing. And by April 2023, over 2 years after, it was growing really well. And these peatlands actually need fire in order for Empedisma to stay dominant. You'll see on the picture behind me, actually, if you've got me on your screen, there's actually things like Banksia and Leptospermum and a lot of other species that exist on the peatland, and they will take over, and they don't form peat in the way that the Empedisma does. So burning gets rid of them. They have to resprout from seed, and it takes a long time. So the Empedisma can maintain the dominance. So these peatlands, although they survive severe fires, they actually do better after the planned cool burns that were typical of traditional Indigenous fire management and is now practiced by national parks and also by Noosa Council. So next slide, please. So this is one way that we determine the peat depth. You get the strongest people in your team to core down and collect the peat cores for analyses. But we also use ground penetrating radar and various other techniques too to go over the peatlands and determine the peat depth. But the coring is essential to get the peat samples. And next slide, please. So here's an example of a core or parts of core. So you can see these cores have a lot of charcoal. All the black is charcoal. And this is not something I've ever seen. I used to work in the peatlands of Southeast Asia. I never saw burnt peat. It just didn't happen. These peatlands never burnt. But these charcoal layers go back thousands and thousands of years. So it's been happening for a long time. So the charcoal actually seems to increase peat storage because it's more stable than the peat. And our analyses have shown that the carbon density of our peat here, the subtropical peat of Gari, it's greater than that of temperate and alpine peatlands, so greater than the boreal peatlands in Siberia and Canada and so forth. And it's equal to many of the tropical peats, so very, very dense carbon. And like other peats, there's more soil carbon stored here than in any other ecosystem. So for any ecosystem in Queensland, this is where we will find the most peat, much, much more than, say, for example, mangroves or other peaty soils that you might hear about. Okay, next slide, please. So I had a postdoc who was looking at the microbial communities of the peat layers using metagenomics, and she found over 4,000 taxa, mostly new species, a lot of pathogenic species actually. And although they decreased with depth, the archaea, which are the methane producers, were more abundant with depth and decreased towards the surface. And we didn't find methane consuming bacteria, unlike in tropical peats, but we did find methanotrophic fungi that could oxidize the methane to carbon dioxide and water. So, but these were only in the shallow peat. So next slide, please. So the problem with this is that if it's at the surface and if it burns, then these methanotrophs will burn. So we don't even know if they consume all the methane anyway. So maybe methane is naturally emitted. This is something we've just started measuring. But there's potentially massive natural methane emissions. But these could be disastrous if there's fire or if there's drought killing off the fungi at the surface. We just don't know. So one of the things we're looking at is what is going to impact potential methane emissions. So next slide, please. So this is the aims of our study. It's very broad. There's a lot of people involved that I'll show you in a minute. So we're going to map the peatlands. We'll determine the depth, how fast the peat's being deposited, how much carbon's being stored. We'll age the peat. We'll look at the past fires. We'll measure the greenhouse gas emissions under different scenarios, pristine peats, degraded peatlands. There's a lot of degraded peatlands, particularly along the Sunshine Coast, where they've been cleared and drained. And we'll also measure the potentially hazardous and climate warming emissions from burning peat. So when peat catches fire, most of the people who are fighting the fires probably don't have adequate PPE to protect themselves, because the particulates from burning peat in Southeast Asia are incredibly dangerous for health. They can enter your lungs and actually enter your bloodstream with toxic particles, so they're really dangerous. So we're going to look into that. And that's what we're going to be doing. And the people you don't have to list the people involved. That was on a different slide. But we have colleagues from Griffith, from University of Wollongong, from University of Vienna in Austria, and also the United States. And we're working together, particularly with Great Sandy National Park and also Noosa Council. Thank you.
Great, thanks, Kathy. So opening up for questions. Naoya, you had your hand up quickly.
Yeah, very interesting. Thanks very much for your presentation. How's that spatial variability in peatland in terms of this whole carbon and potential methane emission drivers?
Okay, so the peatlands are very specifically delineated. So in the sense, although you can find sort of sandy peatlands and things like that, peat itself, where it's proper peat, it will be collected in sort of kind of shallow areas where it gets waterlogged. So it only accumulates where there's waterlogging. So we have it in lakes and in just marshy, swampy areas. And towards the edges, it gets sort of thinner and sandier until it's not there. But they're really very clearly delineated. And I can just about map a lot of them just from looking at Google Maps, actually. I can just see the edges of them.
Right. Are you intending to measure these in the actual peatland, like field conditions, like emissions and things?
Yeah, you saw the guys.
Mm-hmm.
Yeah, absolutely. We've got Sanjeev is he will be using geospatial data, and Javier uses a drone. But most of us go out in the field. I'm going on Friday actually to Noosa National Park, and we will be looking at the peat in situ. It's mostly in situ, and all the greenhouse gas measurements in situ.
especially, and then accounting for these variables.
Yes, and we are working with Mike Ronan. Mike Ronan and I have been working ever since I started work. I used to live in Southeast Asia, and I thought that was the end of my peatland research. But when I came to Queensland, then I discovered the peat, and straight away I was put in touch with Mike Ronan. Somebody just asked about that. So yeah, with wetlands, we've been working very closely.
Yeah, thanks very much. Very interesting.
Great, thank you. Yeah, Liz mentioning Mike, who is an old colleague of mine, much loved colleague of mine.
Yes, very loved.
He is, yes, one of the nicest people in the world.
Yes.
Any other questions to Kathy at this point? No? Well, with that, we might just move on to Professor Fullan Yang. Now, Fullan's last but definitely not least, and he's doing a project on the feasibility of net zero microgrids. So I will hand control over to Fullan.
Thank you, Liz. My project is a feasibility study of net zero microgrid. So the global challenge for the decarbonization is how to reduce the carbon emission to combat the climate change. So energy production is key contribution to the carbon emission. So how can we provide a clean energy? This is quite important. So this project, we use the net zero microgrid to provide the clean energy. So the net zero microgrid contains 100% renewable energy. This includes solar and wind and other source of clean energy. Yeah. So we develop a simulation platform to demonstrate that we can provide such a clean and affordable energy for the power grid. So this work can support Australian net zero emission and provide a clean, affordable, and resilient energy system. So why we need a net zero microgrid? Because global pushing for a net zero microgrid, the country like Australia, US, UK, and even China set like the target to meet the net zero microgrid by 2050. So we can so reduce the carbon emission quite important. So microgrid can provide a local and independent energy. So can integrate all distributed renewable energy into the microgrid and support rural area and industrial and residential area. So this is quite important, and also can provide a disaster promote area. So this is quite important if you can develop such a microgrid. So what are the objectives of this project? So first, we need to build a net zero microgrid simulation farm, simulation platform. So we will develop a data-driven control and optimization algorithm to operate this net microgrid, and then make sure this micro can work in the two model. One is grid connected model, and another is islanded model. So So this is quite important. So if we can do so, we can support the decarbonization and grid resilience. So it's not only for decarbonization, so also can strengthen the power grid. And what a method that we can use in this project. So we collect all the real world data and for example, generation load, weather, and pricing. And then we build a simulation platform using MATLAB Simulink. This is software based. Yeah. So we can reduce the cost to build a real zero microgrid. And then we can apply the data driven and distributed optimization method to operate this net microgrid and enable real-time autonomous energy management. And then we can improve speed, accuracy, and decision making for uncertainty, because renewable is always fluctuation. Solar, wind, and its fluctuation. So we can manage such uncertainty. And expect the outcome. So we will provide a functional net zero microgrid simulation platform. So we based on this platform, we can test a different scenario and then provide 100% renewable energy. And then we can provide advanced energy management technology. So this management technology we can use for deploy more microgrid in future. And technology transfer to industry. So we like to transfer this technology to the industry and then implement this microgrid. So this project hope to support Australia clean energy transition. That's my project. Thank you.
Thank you so much for that presentation and to all the presenters. So have we got any questions initially on this presentation, and then we can open it up more generally if there's any further questions that people have. No? Okay. So first of all, I just want to thank all the presenters, and I think for the people listening today, the scope and the diversity of the projects that are under consideration is really broad and really interesting and really exciting. And so the Hub is really happy to be supporting each of these projects. All of the projects are in their pretty early stages, and the idea of today's webinar was to give people a sense of the work that's going on. And in particular, if you've got a general interest in any of the projects, then please reach out either through me or to the researchers directly, because the research leads are clearly identified on the Hub website, so you can contact them if you've got any question or you've got an interest. And I know that Liz King in particular, where there was some stuff to do with DPI, had some ideas, and I'm sure others of you will have that from your perspective. We've got about 10 minutes left. We can finish up a bit early, but if there are any other questions, happy to take them now. So just opening up the floor to any questions on any of the projects from today. And I'll give people a little bit of time, but if there's not, that's fine. I think there's been a lot of information shared today, and the Hub is planning on having its yearly forum probably in about late September, and that'll be a great opportunity to check in on how these projects are going and developing. But if there's not any questions, which there doesn't seem to be, I just want to thank once again, and if we were in a room, I'd be asking for a round of applause for the amazing, not just the research leads, but the teams that are supporting the work, because one of the really impressive thing about a lot of these projects is that they cut across a lot of different institutional barriers with people working together, which is part of what the hub's really wanting to support. So thank you, everybody, and thanks for taking the time today to either present or listen or do both to these 8 projects. So thank you very much, and yeah, have a great Tuesday.